Ever wonder how engineers design those smooth, satisfying curves you see in roads, especially like those winding mountain passes?
Hmm.
There's a surprising bit of math at play,
Yeah,
and it all circles back to, well, it's the circles.
it always does.
We're going on a deep dive into a fascinating aspect of geometry today. Tangents.
Yeah.
Now, before you think back to high school geometry and like those compass and protractor days,
Right.
I promise this is about to get way more interesting. We'll be exploring tangents with some help from this math textbook, and trust me, you'll start to see how these lines that just graze a circle
Mm-hmm.
hold secrets to motion, angles, and even those perfectly banked turns on a racetrack.
You're right. It's easy to miss how often circles and tangents kind of show up in our everyday life.
Yeah.
The textbook actually uses a great example, a well pulley.
Okay.
As the rope pulls up the bucket of water, it forms a tangent to that circular pulley.
Okay.
And that same concept is at work in so many other places, from the way a train wheel meets the track
Oh, I see.
to how light hits a curved lens.
So we're talking about much more than just lines on paper here.
Definitely.
But before we jump too far ahead, let's make sure we're all on the same page. The textbook does a good job laying out the basics, defining circles and tangents.
Yeah.
But then it mentions that a tangent is a special case of something called a secant.
Uh-huh.
Can you help us unpack that?
Absolutely. Imagine a line slicing through a circle.
Yeah.
That's your everyday second,
Right.
intersecting at 2 points. Now, picture that line moving, gradually shifting closer and closer to the edge of the circle.
Okay.
What happens to those 2 points of intersection? They get closer and closer together
Right.
until eventually they merge into a single point.
Oh, okay.
And that's when you've got yourself a tangent.
I see. It's that fleeting moment where the line goes from slicing through to just barely grazing the
Well,
circle.
that's a good visualization. Okay, I think I'm starting to see how a tangent is like that perfect fleeting moment of contact.
Yeah.
But the textbook doesn't stop there.
It goes on to highlight what happens at that precise point where the tangent grazes the circle.
Right.
And this is where things get really interesting.
Yeah, this is where a seemingly simple rule unlocks a whole world of geometric understanding.
Okay.
The textbook calls it Theorem 10.1,
Oh, yeah.
stating that a tangent to a circle is always perpendicular to the radius drawn to the point of contact.
Perpendicular.
Yeah.
So we're talking about a right angle.
Oh, you got it.
A 90-degree angle.
Yeah, right there where the tangent meets the circle.
Oh,
Exactly. Think back to that bicycle wheel we talked about earlier. The spoke, representing the radius,
Right.
always meets the ground, our tangent, at a perfect right angle.
Oh, okay.
It's this simple, elegant rule, and yet it has huge implications.
Like what? Give me an example. How does this right angle rule actually play out in the real world?
Well, think about those smooth curves on a racetrack.
Okay.
Engineers use this tangent-radius relationship to design banked turns that allow cars to maintain speed and stability. The angle of the bank is carefully calculated based on the radius of the curve and the intended speed of the vehicles.
Wow.
All thanks to our friend, the right angle.
So it's literally about finding the right angle.
Yeah.
But there's more to this tangent story, right? The textbook also delves into how many tangents you can draw from a single point.
Yeah.
And that's where things got a little mind-bending for me.
It's true. The number of tangents you can draw depends entirely on where that point is in relation to the circle.
Right.
If the point is trapped inside the circle, you can't draw any tangents to it.
Right.
If the point is on the circle itself, you can draw exactly one.
Okay.
But if that point is outside the circle...
Then things get interesting. That's when you can draw two tangents, one to each side of the circle.
Exactly.
But here's what really blew my mind. Theorem 10.2,
Okay.
which states that both of those tangents will always be the same length.
Interesting. Right.
How is that even possible?
It seems counterintuitive, but it all comes back to triangles.
Okay.
Those fundamental building blocks of geometry. Right.
Remember we were talking about similar triangles earlier?
Refresh my memory.
Okay.
What makes triangles similar again?
Similar triangles have the same angles, but might be different sizes.
Okay.
They're like scaled up or scaled down versions of each other.
You're right.
And this is key to understanding why those two tangents from an external point are equal.
Okay. I'm following so far.
Good.
We've got our circle, our external point, and our two tangents.
Right.
Where did the triangles come in?
If you draw lines connecting the center of the circle to both the point where the tangents touch the circle and to our external point,
Okay.
you create two triangles.
Right.
And because of that right angle rule we talked about, these triangles are not just any triangles, they're right triangles.
Okay.
And because they share a hypotenuse
Mhm.
and one of their legs is the radius of the circle,
Right.
they are in fact Similar triangles.
So because those triangles are similar, their corresponding sides are proportional.
And that means the two tangent segments have to be equal. It's
Wow.
like a geometric magic trick.
Precisely. And that magic trick comes in handy for solving all sorts of geometric puzzles.
Right.
In fact, the textbook includes a bunch of example problems that demonstrate just how powerful these tangent properties can be.
All right, you've convinced me tangents are way more interesting than I gave them credit for.
Yeah.
But I'm still a bit fuzzy on how we actually put all these properties to use.
Sure.
Can we try one of those example problems from the textbook?
Absolutely. There's one that nicely ties together several concepts we've discussed.
Okay.
It involves figuring out the length of a tangent,
Okay.
and it throws in a chord for good measure.
Okay, hit me with it.
So picture a circle with a radius of 5 centimeters.
Okay.
Now imagine a chord drawn across that circle, splitting it into segments.
Okay.
This chord is 8 centimeters long.
Right.
Finally, we draw tangents from the endpoints of that chord
Okay.
so that they extend outward and meet at a point outside the circle. Our challenge is to find the length of one of those tangents.
That sounds like a lot to visualize. Where do we even begin?
Don't worry, that's the beauty of geometry.
That's
There's
fair.
always a path to the solution.
Right.
And sometimes that path involves drawing additional lines to reveal hidden relationships.
Okay.
The first step is to draw a line segment from the center of the circle to the point where our two tangents meet.
Okay.
We'll call this segment OT.
Okay, I'm with you so far.
Good.
I see the two triangles forming, but I'm not sure what that does for us.
Those triangles are the key.
Okay.
Remember those congruent, similar triangles we were talking about? This is where that knowledge becomes a powerful tool.
Okay.
Because line segment OT bisects the chord,
Right.
meaning it cuts it in half.
Right.
And because we know that a tangent and radius always meet at a right angle,
Okay.
we've created two identical right triangles within that larger triangle.
Uh-huh. I see it now.
Yeah,
We could use the information we already have to unlock the mystery.
exactly.
We know the radius of the circle is 5 centimeters. Right. And because our chord is bisected, we know each half of that chord is 4 centimeters.
Exactly. With that information, we can use the Pythagorean theorem to calculate the length of the segment where OT intersects the chord.
Right.
Remember, the Pythagorean theorem tells us that in a right triangle, the square of the hypotenuse, the side opposite the right angle, is equal to the sum of the squares of the other two sides.
Right. So in this case, we can use the radius, 5 centimeters, and half the chord, 4 centimeter, to find that missing side length.
Yes,
But how do we then use that to find the length of the tangent?
that's where the similar triangles come in.
Okay.
Since we know those two smaller triangles are similar, their corresponding sides are proportional.
Right.
This means we can set up a proportion to find the length of the tangent.
And when we work through that proportion, what do we get?
The length of one of those tangents is 203 centimeters.
Okay.
But more important than the actual number is the process we use to get there.
Right.
See, those tangent properties aren't just abstract ideas.
Right.
They're tools for solving real problems. Yeah.
And making sense of geometric relationships.
That's fascinating. We started with a bunch of lines and a circle,
Yeah.
and by applying these properties of tangents, we were able to solve for an unknown length.
Exactly.
Feels almost like detective work.
It is. And like any good detective, developing your geometry skills equips you with the tools to analyze information, spot patterns, and solve mysteries.
Well, I have to say, I'm looking at circles in a whole new light.
I'm glad to hear it.
Who knew tangents held so many secrets?
And that's the beauty of a deep dive like this.
Yeah.
We start with a seemingly simple concept
Yeah,
and uncover a world of surprising connections and practical applications.
indeed. We hope this deep dive has inspired you to look for tangents in your own world
Absolute.
and to never underestimate the power of a little geometry.
It's everywhere.
Until next time, keep those minds curious.